let's start.
Oh, so I should stop sharing then.
That's fine. Yeah. Hello, good morning. And as always, also good afternoon to our European colleague and good evening to our Asian colleagues. So welcome you to the Source to Sink webinar, the World River and Delta System. So this is this year 2021-17, number 17 talks. We will invite Professor Carol Wilson from Louisiana State University and come here talk about the Ganges-Brahmaputra, the elevation and the sediment dynamics. So once again, I also want to mention, I mentioned this Wednesday, so the International Conference of World Large River will hold kind of hybrid, both face-to-face and virtual in Moscow in earlier August. So we cannot wait to meet face-to-face. We already locked down a year here. So hopefully everything is okay. Yesterday, I just get my first shot of a vaccine. So I will get a second one in 3 weeks. So I'm ready to go. I cannot wait. So although I enjoy this online webinar series, but still I'm looking forward to meeting many of you. And also, you know, it's just simply, you can go to this website, you want to submit abstract. And okay, next week, we have 2 more talks. James Liu from Taiwan, he will talk about the Goping submarine canyon system and coupling the physical and the sediment record. And also next Friday, Sarah from the Art Institute of Chicago talk about the Amazon River POC, particular organic carbon and the source and the fit. The field lab and classroom, I think that's another very interesting talk. Please mark your calendar. And Carol is a graduate original from New Orleans. I think just he back to Louisiana. And so Tulane University, you know, and finally from the humid New Orleans, jump to Boston, get a PhD over there. And then postdoc at Vanderbilt with our dear friend Stu Goodbread, and now is assistant professor at the geology department at Louisiana State University. And as you can see here, Carl is very active on the field, particularly many very known, well-cited paper is Ganges-Brahmaputra, the elevation change, as you can see on the marsh on the delta plan, and also understand the sediment in the river and the sediment transport through the canyon system all the way to the deep sea. So we're looking forward to Carol's talk today. So Carol, now you can share your screen and put the presentation mode.
All right. Thank you, Paul. Thanks so much for that great introduction. I appreciate that. Hi to everyone in your various time zones and across continents. Fantastic to have this kind of webinar series. I'm usually not able to be on here live, but I love that we have a YouTube channel as well, so that people can access it in different times, say if they have a teaching obligation or meeting. And also it's a wonderful teaching resource. So I think that that's been great that we can expose our science to so many different people. Okay, so we're going to talk about the elevation and sediment dynamics of the lower GB Delta. Let me move to the next slide. Of course, this is work that it's not just my work. I've had the privilege of working with incredible people, both here at LSU. I have a couple of graduate students. This is Jeff Bomer here and another PhD student, Leslie Valentine, who's currently with me. Also a suite of colleagues from US institutions and also international. So I've been working with Steve Goodbread. As Paul mentioned, he was my postdoc advisor, but I've been able to work with many of his students, Mike Steckler and Chris Small, Jonathan Gilligan. We're working on other projects together. Kimberly Rogers and Liz Chamberlain. We've got projects now and hopefully in the future. So a big shout out to all these folks that have made this work possible. As the background shows, I'm very much an observational scientist, but I love delving into the theory and what else is out there. And of course, we want to acknowledge our contacts and colleagues in Bangladesh, both at universities, so Dhaka University and Khulna University predominantly, and they're wonderful students. We've been very fortunate to have several of them then move on to graduate school here in the US and elsewhere, like Canada and the UK. And also we want to acknowledge our community members that we go into these locations and regions and we are taking measurements from their soil or from their rice paddies and whatnot, and they let us put our instruments there. So we need to acknowledge them and say thank you so much for everything that they do. Just to put things a little bit into perspective, I'm here at LSU on the Mississippi Delta, very different delta than the GB. I mean, the Mississippi River is only a mile away from me, but and we're very proud of it. It's a big system, drains most of the US, but the GB is very different in that we have that enormous monsoon rains. We've got incredible tectonics, but then also the human dimension of how many people are living on this landscape. So here's just kind of a snapshot of living in Louisiana versus Bangladesh. Sometimes there could be some similarities. So anybody who lives close to a river or a delta could be impacted by regular flooding, either if there are embankment breaches or if the rivers overflow their banks, and which is a very common occurrence. We had flooding just recently in March 2016. And again, here in Baton Rouge, actually in August 2016 was a pretty major flood event here. Regularly in Bangladesh, every year during the monsoon season, there is flooding. So the locals there are constantly dealing with trying to live on this landscape. And I want to point out as well that it's not only the hydrodynamics of the river, but also the coastal environment where we have cyclones, either here, we call them hurricanes. Just last year, we had 6 of them make landfall in Louisiana. In Bangladesh, they did have a really large one, Amphan, last year. But again, those cyclones are helping distribute sediment as well. So this is really important for us to think about. Okay, so I know a lot of you are really familiar with this, but just to remind ourselves, the Ganges is draining the Himalayan forefront. The Brahmaputra drains the backside of the Himalayas. They come together and discharge into the Bay of Bengal. It's a very active delta, as Mike Steckler was talking about just a couple of months ago. We were on a tectonically active margin. But this river system, because it drains the Himalayas, is bringing about 1 billion tons of sediment per year from these 2 rivers, discharging into this Bay of Bengal at the Meghna mouth. About 100,000 cubic meters per second is the water discharge during the monsoon season. It's the 3rd largest in the world. That sediment discharge of 1 billion tons is #1 in the world. So this is a really incredible system. But I want to point out also, so this is a shuttle radar tomography mission, a DEM created from that data. And we can really isolate and bring out several features, like we're talking about elevation in this talk. One is that there are these regions called the Fan Delta that are a little bit higher in elevation. This is where the Ganges and the Brahmaputra first enter into the basin, and they've built out these huge fan-shaped sedimentary deposits. And then as you go further south, there's a break in topography, and we're getting then the really low-lying regions. There's the fluvial tidal delta where those rivers are discharging. Some people call this the Meghna estuary, but it's also obviously the tide-dominated delta here. And then over here to the west is the tidal delta plain. So this is your quintessential tide-dominated system, but we are going to talk a lot about there's fluvial active or fluvial dominated dynamics in here as well, particularly as we transition from the fan delta into the tidal delta plain. The tides are meso to macrotidal, which is what these yellow numbers are showing, that the tidal range as essentially it expands as you go eastward. Also, as you go inland, there's an expansion of the tide as it funnels through these tidal channels, going from 2 meters at the coast to 3.5 to 3, and then it finally peters out where we get this break in topography. So these tides are extending more than 100 kilometers inland. And Rip Hale at Old Dominion, he's got some excellent ADCP and discharge measurements. Just one of these tidal channels, the Shibsha, carries as much water as the Mississippi River during flood stage. So that's pretty incredible. And that's 2 times a day. that the tides are flushing through here. So it's just a really incredible system. All right, want to bring to light the river avulsion throughout the Holocene. Steve Goodbread talked a lot about this, but in general, we have an eastward migration of the Ganges over time, and the Brahmaputra River has a tendency to flip-flop between its two channels. And let's just remind ourselves for the tidal delta plain, because these distributaries are waning and they're no longer actively bringing sediment from the inland reaches here, the sediment's actually reaching this by discharging at the mouth and being advected in from the tides then. The research questions my lab is primarily dealing with are looking at the sediment delivery patterns to these different regions of the delta, looking at how subsidence is affecting these dynamics. And especially we want to think about, we're on a delta setting where subsidence is happening. So we want to compound that with sea level rise to get our relative sea level rise. And looking at what the anthropogenic modifications are to this delta. So here's our talk outline. We're going to do a brief overview with talking about subsidence, flood risk, and the stratigraphic architecture. We're going to look at the Garai River as a focus zone to look at the transition from the fluvial to the tidal zone and some differences in both elevation and sediments. And then talk about the tidal delta plain and future work directions. All right, let's move forward. We know that for delta systems, that delta elevation is really going to be somewhat driven by what the water surface elevations are. For the Ganges and the Brahmaputra rivers, these are the water stages during the monsoon months where we have the highest discharge around August, July, August, September. You can see that these water levels are rising about 5 to 8 meters during that time. They're overflowing their banks. So this flood map over here is showing from 2020, the flood map for Bangladesh. And of course, during this monsoon, we're getting our water discharge increasing from about 20,000 cubic meters per second to greater than 100,000 cubic meters per second. But this water level is overflowing its banks and is building the braid plain in the adjacent floodplain. Now, subsidence is certainly going to be a factor in here. Now, as Mike Steckler showed just a few weeks ago, that this is, again, a tectonically active margin, but we also have a hinge zone where we transition from relatively thin Holocene sediments where our subsidence rates, which are noted in these little yellow lines, are relatively small. And as you go more seaward of this hinge, this is where our sediment thicknesses are approaching essentially 20 kilometers at this point. So enormous sediment loads on here. And these yellow arrows are showing the magnitude of subsidence in these different regions. And again, Mike Steckler has got great data for that. But essentially, we need to keep in mind that as you transition from the hinge zone south, that you expect your rate of subsidence to increase. And Celine Goral has got some really great data that it indicates that our subsidence rates are increasing to about 6 millimeters per year down here at the coast. And we'll talk a little bit more about our recent work and quantification of subsidence, because it's certainly very heterogeneous across the delta front. But let's keep in mind that subsidence, when we compound that with eustatic sea level rise, is our relative sea level rise factor. So I've drawn that out here. So at our coastal area, we're going to be worrying about what the flooding surfaces are doing here. Because this is a tide-dominated system with 2 to 6 meters semi-diurnal tides, we need to think about this water surface fluctuating 2 to 6 meters every day. There's also those storm surges I mentioned that could be up to sometimes several meters high, and those are bringing sediment into this landscape to help build it. And our surface equilibrium is going to be dictated by this balance of our elevation gain that we're going to be getting from our vertical. We've been talking mostly here about inorganic material, but certainly organic accretion from mangroves and any kind of peatlands is part of that as well. And then we have to offset that with elevation loss that could be happening from these rising water levels and subsidence that are creating accommodation space in here. Some previous work that I did with Steve Goodbread looked at the DEM, and we created longitudinal floodplain elevation profiles. I won't go into great detail for this, but essentially we've got several of them crisscrossing the delta. And the important thing to take away from this is this figure here, where the locations of the fan delta, our slope is about 10 to the -4. By the time we get into the lower reaches beyond that topographic break, while we're in our fluvial tidal delta or even the tidal delta, our slope is approaching about 10 to the -5. So it really asymptotes out. And our active braid plane is usually about 5 to 15 kilometers wide that we can document from the SRTM data. So one of the things that we can also draw on, not just looking at those elevation profiles, is the planform morphology. And here's essentially our Ganges, our Brahmaputra over here. We can identify the active main stem braid plane by these dashed lines, you know, the height of when this is overflowing its banks, what areas are getting flooded. But there's some really interesting planform morphology in the Fan Delta where we're seeing a lot of scroll, point bar formations, oxbow lakes. Steve Goodbread and Liz Chamberlain have been actively looking at quantifying the ages of abandonment of some of these distributary channels. So they've got some great data in there, but it's quite interesting to think about. We have a planform morphology where these channels are showing that they've been relatively active in the geologic past, whereas when we go beyond that topographic break, our distributary channels are really stable and there's not a lot of evidence of lateral migration. So that begs this question here: how do these morphologic regimes control sediment deposition patterns? And I know you all are very familiar with it, but just as a reminder, and if you haven't read Man Liang's results from her delta reduced complexity model, she's got some really nice figures looking at delta development and what kind of stratigraphic architecture you would expect with varying subsidence rates. But in our fluvial reach, we expect to have more lateral migration. There's various tabular sandy deposits. And as accommodation is being created and the rivers are sweeping laterally, any kind of mud floodplain deposits are essentially getting obliterated and picked up and removed. And the channel belts are likely overlapping and multi-story. Whereas when you go into areas that are in the deltaic reach, where there's likely higher subsidence or accommodation space being created, there's less lateral migration across the floodplain. These sandy channel belts are isolated and vertically offset, so single story. Okay, so as we look at that morphology, I want to show some data that actually Steve Goodbread and some of his students have been working on, but it's been something that's been kind of fascinating to me, of this upstream to downstream transition and what the stratigraphy is showing. So Steve showed a lot of data from his, the borehole data from the BanglaPIRE project, if you recall his talk from before. There's several, I mean, it's an immense data set. There's more than 300 boreholes that have been drilled across this delta. They go down to more than 90 meters depth. And this spacing allows for a really detailed stratigraphic coverage and analysis of the Holocene. So I want to focus on a couple of transects, A, G, and P, that capture this downstream transition. So transect A was Jennifer Pickering's PhD work up here in the fan delta of the Brahmaputra. I'm just going to kind of zoom in over here. This is the stratigraphy, and just to orient you, all of these are the individual borehole logs, where the orange is medium-sized sand, the yellow is fine to very fine sand, and the gray is mud. So just to kind of like orient your eye to our Brahmaputra Valley in here, Paleo Valley. So this dashed line is the demarcation of the Pleistocene to Holocene. So right through here is where the Brahmaputra, current Brahmaputra is existing. And it's a really coarse grain sand that's accommodating this. So a really river-dominated bed load through here. Now, as we transition downstream to G, this is Megan Patrick's master's thesis, and she and Steve are working on a publication now from this. So again, G is lower down here. We're below that topographic break. There are several valleys that are captured in this, but we're going to focus on again on the Brahmaputra Valley just to keep it consistent. And again, G at depth, even though we're looking at depths of 90 meters or so, only maybe the upper 4 or 5 meters is there mud preservation. Predominantly, there's still a lot of orange here, so a lot of medium to coarse sand, some fine sand, a little bit of mud. But again, really sandy substrate. And it's not until the upper units that we see a little bit more mud. And it's not until we get all the way downstream to P, which these are cores from Polder 32. When again, we look at depth, we are still seeing the sand, but you'll notice there's not nearly as much orange in here. So we've lost a bit of that medium to coarse sand. And one thing that's important to note is in the upper 30 meters or so, we're seeing a lot more mud and a lot more mud preservation. And there's some evidence of channel bodies that are isolated and preserved in there. So we interpret this as this bottom is our bed load, the river dominated when this river was filling in the paleo valleys. Eventually, as sea level continued to rise and the river avulsed away and it became more of a tide dominated reach. This is really our tide dominated stratigraphy that's being preserved. So this finer stratigraphy in the shallow subsurface is indicating that we're probably having more compaction and dewatering and helping to explain a greater subsidence rate that we're seeing below that hinge zone. But of course, as Mike Steckler pointed out, there's not only shallow subsidence, there's not only compaction of this, there's also loading of the sediment on the lithospheric plate. So that needs to be quantified and investigated further. Okay, let's transition from the fluvial to the tidal zone, and we're gonna look at the Garai River distributary. I'm gonna first start off showing the difference between the Garai, which is a waning distributary, to the main stem channels. So the Garai is a distributary of the Ganges that offtakes before the Brahmaputra, and it discharges into the Sundarbans in one of the tidal channels. The main stem channels are highly dynamic. This is a great paper by Tess Jerial, where she used Landsat images and created a program called River Map to document where there's been erosion and accretion of the channels. So red in here is erosion and blue is accretion along the margin. So obviously the main stems are really dynamic, but it begs what's happening, once these older distributaries that were once very active, once they're waning, what happens to them? And I'm also very interested in the role of the backwater. I know a lot of you guys are interested in that too. So this seems to be kind of a really neat location for it. I just wanted to point out my student Leslie Valentine is working on this active Meghna estuary, and then we're going to look at a little bit of her data here later on. But first, we're going to talk about Jeff Boehmer's work, who's looked at the Garai and also the Sundarbans. Okay, just so that we're all on the same page about what the backwater is. I think everybody here is very familiar with it, but and I'm learning myself. But the backwater is essentially where we have a separation from normal flow conditions, where the water surface gradient is approximately the same as the channel bed gradient. Now, as a river discharges into a receiving basin, and in our case, it's sea level, so the elevation is going to zero, the water surface asymptotes and that water surface gradient ends up decoupled from what the channel bed gradient is doing. And folks like Jeff Neutrauer on the Mississippi River system, which is what this graph is about, where we're looking at river kilometers upstream. This is our channel bed elevation. This is the water surface elevation at low flow, the water surface elevation at high flow. There's obviously a very different change in water discharge. And then of course, then the sediment mobility changes. So he showed that on a seasonal basis, the bed load sediment mobility really increases. There's also an interesting change in planform morphology. Blum showed this, but it's really work from others, Jeff Neutrauer and all, and lots of other folks have worked on this. But upstream of the backwater, these reaches where the channel is very laterally mobile, and we see scroll and point bar formations and oxbow lakes, et cetera. Downstream of the backwater, we're seeing isolated channel bodies. So a single thread channel, there may be an avulsion, like this is the Mississippi River lower, and here's Bayou Lafourche that offtakes, but it's channel bodies, and they are separated by interdistributary muddy basins or peat-dominated basins. The channel belt thickness decreases once you go into the backwater, and also the lateral migration of the river decreases. So Jeff studied, Jeff studied these effects along the Garai, where we not only have the fluvial impacts, but also we're getting into tidal as well. So we have elevation transects that we're taking from upstream the Garai to the downstream reaches. He's capturing both fluvial, mixed, and then tidal dominated regions. Along these, there are point bars that he has then sampled with core transects, and he's done detailed stratigraphy, analyzed the grain size changes where we can take a look at the spining and mass extraction of sediment. And again, he's looked at lateral migration rates along these particular reaches. So I want to show you some of his results that he published in the journal Water a couple of years ago, where this is a profile, elevation profile, like we've been seeing before, where I'm going to orient you that this is river kilometers from the mouth. So these are the upstream reaches. This is the downstream. The black is the SRTM raw data. The green line is the 10-kilometer running average from which we can calculate slopes. So he has our slopes up here of about 10 to the -4 in that fan delta region. There's an abrupt elevation shift, and down in that tidal delta plane, he's getting a slope of about 5 times 10 to the -6. So very, very low gradient down here in comparison. Now, in addition, Jeff was able to obtain from our author Pethick some raw bathymetry from the Garai River. So this red dashed line is the channel bed depth. So again, this green line, this is the subaerial surface elevation. This red dashed line is the channel bed. And then the blue line here is a 10-kilometer running average of the bathymetry. So it's very interesting to note that we have this elevation shift and also transition into the backwater about the same zone, about 150 kilometers upstream from the river mouth. Now, this is a summary figure. I'm not going to go into great detail of all of his cores, but again, I highly encourage you to take a look at his paper. It's great. So he's kind of lumped in here what we see in the fluvial dominated zone with the core stratigraphy, what we see in the mixed energy zone, and what we see in the tide dominated backwater zone. He analyzed with the cores the sand content. So this is essentially the fluvial dominated zone. There was an up core fining. So essentially we've got a fining that's expected from point bars. But the sand content, as we analyze this from upstream to downstream, is very interesting, where in our fluvial dominated zone, we've got 80% sand. That immediately diminishes down to about 50 to 30% sand when we're getting into our mixed energy transition zone. And here's just kind of a generalized stratigraphy we might expect. And so you notice that a lot of that yellow, which is sand, is much smaller. We're seeing a lot more coarse silts and medium silts preserved here. And then by the time we get down into the backwater zone, our representative stratigraphy is all silt, very little sand, if any, that makes it down this way. At least on the point bars themselves, and there's evidence of tidal lights through here. So very interesting to see that. And we noticed, again, it's not only the upstream limit of the backwater, but I put on here the upstream limit on the tides, or we put on here that, because this is not tidal incursion this far inland, 200 kilometers, but this is water level fluctuation. So it's still a backwater effect, right? The tides that are happening downstream are backing up the water so that the unidirectional flow is slowing down and speeding up. And we are hoping to be able to capture this in some future research with Rip Hale and Jim Best and all. Should be a lot of fun. Okay, in addition, what we're seeing in the system is very similar to the fluvial dominated. We got our channel migration rates relatively, I wouldn't say zero, maybe about 7 meters per year in the fluvial dominated, really increases in our mixed energy zones. And then it diminishes down into the tide dominated. So really stable channels down here as well. So great data. Okay, our tidal delta plane. Let's talk about our impacts of anthropogenic modification. I'm gonna grab a sip of water really quick. Okay, Paul, this is for you because I know you're really interested in the canyon system.
Thank you.
So before we start talking about the tidal, we got to kind of understand where this is coming from, right? The GB is discharging 1 billion tons of sediment off here. And a lot of us have been working to try to figure out where the sediment is going, right? Many authors, this is just a few of them listed here, but we can close the gap a little bit. Based on some authors are showing that up here in the subaerial floodplains, close to the river, we're capturing about 30% of this load. Off here in the subaqueous delta, maybe about 40% is being captured here, and that's just incredible. We don't even see it, right? But this is this offshore cliniform. Kimberly Rogers has shown that about 10% is being advected back inland into the tidal dominated delta plain. This is the Sundarbans where you see all this green right here. And so if we do kind of a balance, then that leaves what, about 20% or so that is then being shunted off into the canyon and then into the deep sea fan. So we're gonna just look a little bit at the subaqueous delta and the canyon first, and then we'll go to the tidal delta plain. So again, a lot of sediment coming to this region. In fact, the subaqueous delta, some argue it's the youngest and the most active, like the largest accretion that's happening in the delta is happening here. Because accumulation rates are on the order of 5 to 15 centimeters per year. That's measured right at that forceps out here. In fact, here's some sub-bottom profiles that Steve and some of his colleagues have collected. I think Kimberly Rogers was on this cruise as well. The blue line is this top one, red line is the middle, and then the yellow line, it cuts across the canyon. But essentially, these images are documenting the cliniform of these forceps right here. So massive amounts of sedimentation happening there. And Palamengi showed that the cliniform is prograding across the shelf at 15 to 20 meters per year. So that's incredible. The canyon itself has rapid accretion happening, 20 to 50 centimeters per year of material that's getting loaded into the canyon head. And Kimberly Rogers and others documented really well in one of their papers all of the gullies that cut across this area and, you know, essentially feed into the canyon head. And there's a lot of mass failures that, you know, sweep the material further on down, right, with turbidity currents and such. And there could be triggers like earthquakes could be triggering these events, cyclones could be triggering them. There's also some evidence, I think Kimberly mentions, about some groundwater fluid moving through that could also be triggering that. So it's a really complex system, and we obviously still need to learn more about it. And I think, I don't know if Steve is on, but he mentioned to me there was supposed to be a cruise this year to go out to this region and core some more and take some more measurements, and it was canceled because of COVID and the boat, and really kind of a bummer. Anyways, okay, so let's go into this tidal delta plain, right? So material that's being advected back inland to this area. Steve kind of gave a little bit of an orientation, but if you missed that talk, I'll orient you. The Sundarbans, again, is here. This is a natural mangrove forest. In fact, it's the biggest mangrove forest in the world. These yellow lines here are the polders. They are embanked areas. So these yellow lines are individual levees that have been built, or they're earthen embankments, earthen levees. So about 5,000 kilometers has been embanked down here. It's pretty incredible. And they were built, obviously, similar to other deltas, to protect people from flooding, protect them from cyclone storm surges. But really it was that salinity during the dry season that's in these tidal channels. And they realized if we can put these embankments up, we can keep the landscape inside them fresh year round and bolster our agricultural production. So that was one of the reasons they put them up. It was highly successful for the agricultural production. In fact, the population boomed after this, after these were built in the 60s and 70s. But unfortunately, there have been some really negative impacts, particularly for this delta plain that normally requires sediment. So we're actively studying the Sundarbans versus the Polder regions. I grabbed this diagram from Rip Hale, got to give him credit, you know, nice and clear to show. During the low tide, our Sundarbans platform is subaerial with our nice mangrove forest. High tide, however, the tide overflows the platform, it's inundated. Here's our Bengal tiger there. I've never gotten to see one in person, but we did get to hear one and capture its pug mark the next day right next to our site, which was really exciting. But when you've got people out there and you put the polders up, it impedes that regular tidal inundation, right? So at low tide, the water in the tidal channel is very low. High tide, however, that water is no longer overflowing this landscape and supplying sediment and material that could be in equilibrium and keep pace with that. And as a result, these elevations end up losing ground. This was very well documented by Leslie Auerbach in a paper in Nature Climate Change. This was part of her master's work at Vanderbilt with Steve Goodbread, where she performed, in addition to cores, but she took elevation surveys. So I'm going to kind of orient you. This is kind of a busy diagram over here on the upper left, but these dots are elevation surveys from an RTK, where she's outside of the embankment here on these riverbank terraces. Here are the embankment heights, so various heights, obviously, depending on where you are. Here is inside the polder and then a transect inland. So the polder elevation is quite low. So if we look at these numbers, we're looking at about 1.5 meters in this EGM 96 datum. Whereas the Sundarbans is sitting right up here. So she has some elevation surveys across the Sundarbans as well. And they're sitting up here at about 2.6 or so, which is approximately mean high water. And if you know wetland dynamics, when you're on a wetland landscape, that wetland can grade up to mean high water, because that's what's flooding the landscape and supplying the sediment. Or if you're in an area that's is very close to the coast, you could have storm surges that are helping that. But for the most part, this is our floral zone. This is where the Sundarbans exist. But since the polder is this much lower, that tells us that there's been 1 meter to 1.5 meters of elevation loss that has occurred in all of these polders, which equates to 2 to 3 centimeters of relative sea level rise. And as Steve mentioned, this could really exacerbate the flooding should an embankment fail, like what happened in Cyclone Isla, where a few of these embankments at several polders happen. And, you know, if the high tide is up here, these people are being inundated with 2 meters or so, 1.5 meters or so of water 2 times a day. So it took them 2 years to repair the embankments after Cyclone Isla. Pretty incredible. Okay, but I want to bring to light also another problem in this delta. Because of poldering, not only do you have the elevation offset inside the polder, but there's now no longer a place for the water to flow and inundate those huge intertidal platforms. So a lot of that water has been diverted into the channels, and Pethick and Orford really nicely documented that the tides have been amplifying over time, and they attribute this to poldering. So what that means is he has water levels from Kulna and Huron Point for comparison. So Kulna is about 100 kilometers inland. Huron Point is down here. In Kulna, the area where we're really close to the poldering, this is the mean high water marks over years. Monthly mean high water. This is monthly mean low water down here. He's drawn lines through here to essentially show that there's been an amplification of that tide. And the important thing to note here is for people who live in tidal deltas, tide-dominated deltas, it's not what mean sea level is doing. We always talk about eustatic sea level rise and relative sea level rise. Well, if you're in a tide-dominated delta that your tide is being amplified, it's this effective sea level rise. You've got to account for the tidal amplification as well that may be happening. And this is because of anthropogenic activity. Where we're looking at 1 to 2.5 centimeters a year of effective sea level rise when you take into account not only eustatic or subsidence, but you also add that tidal amplification in there. And that's got great implications to all of this. So it brings to light some questions that we had in our research lab of what is going on inside the polder. Are those elevations continuing to decrease? Is there elevation remediation possible? Is the natural Sundarbans that's outside, are they keeping pace with relative sea level rise or this effective sea level rise? So I'm going to show you some work from my student Jeff Boehmer comparing the Sundarbans with the poldered landscape. And I'm going to mostly focus on the Sundarbans today. But we use an instrument called a rod surface elevation table, which is a rod that's been driven down to refusal. It's about 80 meters or so depth. 80 feet, there we go, let me get to 80 feet, so about 15, 20 meters. There's an apparatus that's put on the surface and these little pins are lowered. And we can get the elevation of that surface during that time of measurement. And the idea is you come back 6 months later, a year later, whatever your time frame is that you want to get that measurement. And you can get millimeter scale elevation change. This has been developed by Don Cahoon at the USGS. And in Louisiana alone, there are over 300 of these scattered across our marshes. Worldwide, there's over 1,000. And these are the first ones that have been installed in the GB Delta. So we're really excited about the data that's coming from them. Okay, so that gives us elevation change, but we also are interested in that vertical accretion. How much sediment is being deposited on the surface on a seasonal basis or yearly basis. And we use marker horizons for that. And then we can also calculate a shallow subsidence. So what we do is we document elevation change over time that you're getting from the RSET, the vertical accretion over time that you get from the marker horizons. And if there's some kind of offset, a difference, that's our quantified shallow subsidence during that time frame. Okay, so we have several RSETs that have been deployed here in the Sundarbans I'm showing. There's several in, this is Polder 32 right across the bank. In the Sundarbans itself, I'm just going to jump straight to the data, and you can read it in Boehmer's 2020 paper in Katina, where this top right is showing our surface elevation relative to the baseline, and we divide our sites into stream bank sites and interior sites. And this is very customary in wetland science because we usually, at the stream bank, we do expect to see a little bit greater accretion and elevation gain happening in the formation of a natural levee, versus more interior sites might not receive as much sediment. And that holds true in this system. We also do see with our vertical accretion that we're measuring using sediment tiles. These are bathroom tiles that we place down there. We actually found that bathroom tiles work better in the system than like marker horizons, like a feldspar horizon, just because of bioturbation is very active here. So here's our vertical accretion. So you'll notice here, if we look at these two graphs, that this vertical accretion is outpacing this surface elevation gain. And so that gets us our shallow subsidence, right? So the elevation gain is on the order of about 1 to 2.5 or 2.1 centimeters per year. And it's pretty incredible how much material gets deposited in these mangroves, by the way. This is one monsoon season and how much sediment was deposited. One time we went out there and there was over 4 centimeters of sediment that was deposited. I mean, incredible system, so much material. So again, we can calculate the shallow subsidence. And that's what this graph over here on the lower right is showing. I apologize that the text appears to be cut off, but this is our shallow subsidence relative to the baseline, where any number up here is subsidence is happening. So there's a compaction of the material. Anything over here is actually swelling. And it's interesting to note that during our monsoon season, we are seeing evidence of swelling of the soil, and during the dry season, compaction of the soil. One of the things that we are able to elucidate with looking at some core data and also groundwater piezometers is what the groundwater is doing, like how much water content is in the core, and then also just marking what the water levels are doing. So here's some shallow piezometer data for our 2 sites. Imagine this dashed black line is the surface of the wetland, the mangrove. Anything that comes above this is when the platform is being inundated by the tides. Again, the gray shaded is the monsoon season and the white is the dry season. And it's fascinating to note that during the dry season, our water surface in the subsurfaces, our groundwater is lowering up to 1 meter. So that is oxidizing the subsurface, and we're seeing, again, low water contents during that season. We're also seeing very low organic material preserved then because it's likely being oxidized. And here's some data that we've collaborated with Rip Hale of calculating the hydro period during these different seasons. But again, really fascinating system. Brings to light how tidal inundation, the seasonal tidal inundation, the seasonal supply of sediment, and then also what is happening during those dry seasons is really important to that elevation dynamics and also if there's any shallow subsidence. So if we compare the natural rates of our elevation gain versus our relative sea level rise rates. Jeff has documented this with the green line that's solid is our stream bank sites and those elevation gains. The dashed line is the interior sites. The red line here is the rate of relative sea level rise that's been documented for this delta from several authors. And you'll notice that these green lines are exceeding that red line. In fact, they are pretty much tracking or surpassing effective sea level rise that Pethick and Orford documented. So that's why we say the Sundarbans appear to be tracking this, and that makes sense. If the mean high water is flooding the platform to higher inundation depths, that gives an opportunity for more sediment accumulation to happen in that zone. But it's important that effective sea level rise is an important component to our platform dynamics. And we're also putting in here that it's reliant on adequate sediment input. If you notice before, we showed our vertical accretion rates were mostly inorganic material. You've got to have that sediment to be able to build this surface then. Okay, what about the human altered system? We're seeing, actually, it's quite interesting, a much larger elevation gain in some of these regions. That makes sense because it is lower in elevation. We did have some edge effects, I will say that. So some of these sites that I have documented here are located close to a sluice gate. So they actually were receiving some sediment from the sluice gate getting into that. And we have since placed some of these SETs in a more interior site to try to get away from those edge effects. And one of the students from Bangladesh, Dhaka University, is working on her master's on this particular work. So stay tuned. Okay, I want to bring to light another anthropogenic impact that's happening from poldering, and it has to do with the tidal channel network. Paolo Pasalacqua did a really nice paper documenting the distributary channel network out here. So all of these blue lines, this is our delta. Here's the Meghna mouth. Here's our tidal delta plane. All of these lines are demarcated the channels through here. So very dense channel network on the tidal delta plane. And there seems to be a decrease in connectivity as you go upstream near Kulna. Well, there's something that I stumbled across, and I wondered about the effect of poldering on this creek network. If there was any kind of difference that we could see between the Sundarbans, where it's unaltered, versus the poldered regions. And indeed, you really can. So first, I'll show you the Sundarbans. Really simply, this is just a couple of areas showing 1973, what the channel network looked like. You can see it's very dendritic, very complex. We have some smaller order tidal channels that look like this on the ground, but those are the ones that are actively flooding and draining the platform. And then we have these much larger order conduit channels bringing the tides to and from. 1973 to 2013, not much change in there. So really stable in the past 40 years. But if we look at the poldered areas, well, you know, when you put a polder up, you change things in a couple of ways. First of all, any creek, tidal creek, like a lower order tidal creek that was inside that area has now been cut off. Sometimes they do have sluice gates and regulators, but it's very highly regulated and not much water flow goes through them anymore. So I noted and quantified out how many channels were cut off when they did the embankment creations. And then I also documented those channels that were outside of the polders, what happened to them. And it was, Steve touched on this, it was really fascinating. We just kind of like stumbled across this. And there were eyewitness accounts from the locals saying, wow, our tidal channels are really silting in. It's causing a huge problem with our navigation. What's happening? So this essentially was quantifying that, where we could see from the imagery creeks that were more, or tidal channels that were more than 300 meters wide were silting into less than 20 meters wide, and we filled in like several meters of sediment. And the locals use this land for, they call it kosh land. So they either use it for agriculture, for rice paddy cultivation, or shrimp aquaculture. So here's a picture of a tidal channel that's been cut off, and now here's a shrimp pond. Here's two regions. This particular reach, you can see this dark white lines. That's where the embankments used to be. So the tidal channel was literally that wide, or just a little bit inboard of that. And everything that's green in here has silted in and has now become shrimp aquaculture. So quantifying these numbers was just mind-blowing to me, where by poldering, about 1,000 kilometers of low order creeks were obstructed. In addition, those higher order channels that are outside of the embankments, more than 400 kilometers of them have filled in. So navigation can no longer move through them. More than 90 square kilometers of new land essentially has been built through here, which is now termed kosh land to be used for agriculture and aquaculture. And what this amounts to, it's quite incredible. So in terms of like these sediment budgets, Kimberly Rogers, again, I mentioned that she documented in the Sundarbans, 10% of the GB load, which ends up being about 62 million metric tons. We document up here, this is 12 million metric tons that has infilled this region. So it's really incredible, how much sediment that's coming through this region and then being deposited in these regions that it wasn't even accounted for previously. So that's 15% of the total mass, total sediment mass deposited in the Sundarbans here. Okay, let me wrap this up and just talk about some future directions related to what we were just talking about with those channels silting in. Well, it's a problem to navigation, right? And the locals know that, and they are actively trying to correct for it by dredging. So this is some pictures from a couple of different channels in Khulna and Rampal, which is in the southwest region of Bangladesh. And here's an active dredger that's pumping up sediment from this, and there's a pipeline, so it creates a slurry, and then it discharges it and dumps it adjacent to the channel. In fact, you can see a lot of sediment through here. So they're physically widening and opening these channels now. They realize they need to open this up and help with the navigation. And also that channel siltation has caused a lot of waterlogging problems as well. They can't drain their polders very well. So this is their solution. Unfortunately, their solution includes just dumping material right along the banks. And the next monsoon comes through and a lot of that material just sloughs back in. So here's Khulna 3 years post-dredging, and there's sloughs of material still around. I've been to a place called Tala where the material was actively just going right back into the channel. So one of the things that Leslie's been looking at is the elevation differences between a couple of these areas as you go upstream to downstream, and then also what happens to that or how much siltation of the channel is happening. So first I'll just show a sneak peek of her elevation gradient data. So we're looking at Khulna up here and Rampal down here. We expect there to be a bit of an elevation gradient. Here's a stratigraphic cross-section when you're outside the embankment, what you might see versus inside the embankment. Predominantly very silty both outside the embankment, also inside the embankment. Some of this is showing sandy silt, so there can be a little bit sandier material. We know from some deeper cores that we've taken in this region, like with Liz Chamberlain, that you do eventually hit some sand where the former channels are. But again, I want to bring to light how sandy it is, and then I want to bring to light also these elevation offsets. So outside the embankment where it's still connected to the tides, even if there's a point bar and cut bank, our point bar might be a little bit lower in elevation, our cut bank's a little higher, but you're still talking about elevations about 5 meters relative to EGM 96. Whereas inside the embankments, so many of these places we're looking at only like 2 to 3 meters. So again, huge elevation offsets because sediment is no longer coming into these regions and allowing that vertical accretion for the elevation to maintain itself relative to the tides. Now, relative to the tides is really important. So this is a little bit busy. This is Khulna and Rampal. The blue box here at Khulna, this is the unembanked elevation on average with the, sorry, what do you call these? The boxes of percentiles. Here's inside the embankment. So meter and a half lower. Rampal, it's the same. Outside the embankment, relatively higher. Inside the embankment, much lower. But what Leslie's been doing is also relating this to the tides and those tidal elevations, where inside these embankments, they right now are below mean, the monthly mean high water. So this is using tide gauge data. So this dark gray top of this line would be our monthly mean high water. Down here would be our monthly mean low water. So right now, if the embankments fail, these folks are underwater. The thing that's more critical is, as we were mentioning before with Pethick and Orford saying that there's an amplification of the tide. And if you continue that out, she's calculated out what will be the mean high water in 2050, so 30 years out from now. So if nothing is done, these folks, say here at Rampal, will not only be inundated by, I don't know, 1/2 meter of water, but now they're going to be inundated by 1 meter or 1.5 meters of water. So essentially the problem is bad and it's only going to get worse is kind of the take home message for that. And kind of, fun data, she's showing some preliminary results of how you can repurpose this material, either raising houses or creating new embankments. So really fun data. It could be really impactful if we repurpose this dredge boil, essentially. And I'm gonna finish up with just a very sneak peek. Mike Steckler mentioned this, where we're working in conjunction of coupling our RSET networks, which measure shallow subsidence, to the GPS, the continuously operating GPS networks that Mike Steckler has. Again, these help us get together both shallow subsidence and deep subsidence. Because if we're getting the GPS and the RSET, from the RSET, we're getting our sediment accretion, our elevation change, and our shallow subsidence. Here's just a little diagram of our RSET. Here's a GPS that we've placed on here, and this is getting we're going to be able to get the total subsidence when we do these kinds of calculations. So right now we've got some students in Bangladesh, Pinky and Masood, that because of COVID, they've been incredible. They've been able to go into the field for us, continue these measurements. They are getting vaccinated, I think, in the next couple of weeks, and they're hoping to get back into the field in April. So that's been great to have them. Okay, I'm gonna wrap this up with just some concluding remarks that I hope, if nothing else, you've seen that this delta in general, but the tidal delta plain even, has got incredible landscapes that are both subaerial and subaqueous. You do need to take into account whether or not you're in the fluvial, the tidal, the mixed zone, because there's a lot happening in those different zones. Anthropogenic modifications have had really significant ramifications in this delta relative to the elevation dynamics, the tidal hydrodynamics, and the sediment distribution. And I put on here, connected landscapes appear to be tracking effective sea level rise. And again, connected is if it is connected to the tides and if there is adequate sediment through there. So we do need to keep into account the damming and such that might be happening upstream that could be affecting the sediment supply to the delta over time. But this parameter, this effective sea level rise, is really important for looking at the overall sustainability of the delta plain. All right, and I will, at least for students, show this slide so that they can have some references in case they're interested, and I'll stop there. And thanks so much for your time.
Great, Carl. Carl, that's a fantastic talk. So now we understand the lower Ganges Delta, Brahmaputra Delta better and better, I will see. So with this couple more talks, and so we can really put together as a collection, So anyway, yeah. If you have questions, please go ahead. I know some of you have to leave. So please go ahead, jump in, and don't feel shy. Unmute yourself.
Or should I be paying attention to the chat? Oh, there we go.
So John, go ahead. Yeah. Are you able to unmute yourself? Yeah.
Hi, Carol. Fantastic talk.
Great to see you.
Yeah, great to see you. It's really one of my favorite papers, your paper showing the network rearrangement due to poldering. I guess my question is about the channels that aren't infilling. Do you have any idea of whether they're remaining quasi-stable or they're growing or anything like that?
Awesome. Well, first of all, thanks so much, John. That's really kind of you. I appreciate that. And it really was something we stumbled upon and was like, wow, this is really cool. But great question. From what I analyzed, a lot of the infilling channels are dead end channels. Like they were conduit channels before. Then with the embankments that they placed on them, they essentially had nowhere to go. The water had nowhere to go and they became a dead end channel. So the tidal velocities diminished and whatnot. Great question about the remaining channels. And I wondered that myself. And in fact, Steve Goodbread's student, Rachel Bain, recently has got a paper that shows when you relate, so there's two big tidal channels, the Rubsha and the Shibsha, that supply water to this region that we're working in. And in particular, the Shibsha, there's all these cross channels between the two. There's like, I think 3 of them. And those, while all these other channels surrounding them have filled in, those have remained open. Rachel does a really nice job, and I think a paper she did in 2019 to show that the water in the Shibsha is now being diverted into the Rubsha, and there's so much tidal flow. It's like capturing now what the Garai that comes down, and it used to flow into the Pushur. So now what used to flow downstream from the Garai into the Pushur is being offset into the Shibsha and flowing down through there. So some of these cross channels are staying open and even widening because of this shift in where the water is going. So yeah, I highly recommend you check out her paper. It's fantastic. I think it's Rachel Bain, Steve Goodbread, and Rip Hale. They did some great ADCP surveys along those necks.
Yeah. I'll go back and read that one. Thank you. Thank you.
Yeah, great talk. No, absolutely. And you know, I can send it to you too. I have your email.
Michael.
Hi, Carol.
Great talk, putting all our stuff in context. And there's actually something that you don't know. Remember when we were at our compaction meter in 2015 and they were dredging it? When I went back there with Liz Chamberlain in 2017, we saw that at our compaction meters before they collapsed, the sedimentation rate went from 1 centimeter per year to about 4 or 5 centimeters per year after they dredged.
Wow. So once they dredged, they reconnected, allowed more water,
a lot more flow,
a lot more sediment.
Right.
Wow, that's incredible. What was that? Are you guys measuring that sedimentation based on like those concrete platforms that you all had there and trying to figure out how much was on top of this?
We embedded a little steel plate in each concrete platform to make the measurements from, to see how much friction there was. I'll send you some figures, some pictures.
Yeah, that's great. Well, Mike, you'll be interested. Actually, one of those channels that Leslie is doing her channel infilling on and the dredging on is your compaction meter channel.
Mm-hmm.
So that's great.
My poor late compaction meter.
I'm really sorry about your compaction meter. I know. May it rest in peace.
Yeah, but Scott DeWolf is finishing up the paper on it.
Oh, great. Yeah, it's excellent data, right? And if memory serves, that paper really shows that a lot of the compaction is happening in the shallow subsurface, right?
Yeah.
So awesome. Great. MD, I know you have a question. I know you're from Bangladesh.
Hi, Mohammed.
Hi.
Rafiq.
I already wrote him. Carol, thank you for very nice presentation. I have a question or suggestion like this. You know, last year or every year we face cyclone which damaged our embankment. Usually last year, you know, some area of Bagherhat already inundated during the cyclone, and still the embankment is not reconstructed. So is there any effect of cyclones on sedimentation of the region?
Thank you so much for that question, and great to have you. Great to have a local from Bangladesh joining us. That's great. Well, I'll ask you after I answer your question, like what affiliation you have. But it's very true. So when a cyclone goes through, where there are embankments, it could like embankments fail from various reasons. We know it could be overtopped. There could be undermining, like essentially it scours underneath and then there's a failure of the embankment. We also know that the stratigraphy in that area indicates that, you know, these areas where they had a tidal channel that they cut off with an embankment, that stratigraphy is likely based in sand because it was a former channel. So it's probably a very sandy substrate. And so that sandy substrate, even if it's a little linear strip, It could be a source of subsurface piping underneath the embankment. In fact, one of the embankment failures in New Orleans, the one that hit my house, was because of that exact mechanism, that it was a sandy layer in the subsurface that water was able to percolate through because of the pressure head gradient. So when an embankment fails, certainly there can be an immediate sedimentation event, right? It's almost like a crevasse splay of sorts that could happen. But from what I understand, and I'd love to learn more about it because I've never personally been there when these embankment failures happen, but from what I understand is certainly you're going to have the immediate effect, the immediate failure, but then because this is a semi-diurnal tide, that the tides come up and down twice a day regularly, that it's that tidal pumping, that if that embankment breach stays open, it's that tidal pumping that is really effective at moving sediment from the channel into the polder and depositing sediment. Leslie Auerbach, in fact, in her Nature Climate Change paper, documented that after Isla, Polder 32 accreted about 20 to 30 centimeters on average of sediment per year because of that tidal pumping. But you're right. So Cyclone Amphan, there were so many breaches from that. And I'm sorry to hear, this is news to me, that they haven't repaired the embankments yet. So I'm sure some areas are still being negatively impacted by the tides. Then it's, I don't know, then it's kind of like a mixed blessing. Maybe that sediment that comes in will help ameliorate their elevation, so they may not be as vulnerable in the future, but it still makes their livelihood hell right now while it's happening.
Yeah, it's too bad COVID stopped you from going out after Amphan to make measurements.
Right. So is it Shofikul? Is that how you pronounce your name?
Yeah.
Where are you from, Shofikul? What affiliation?
My affiliation is Shahjalan University of Science and Technology, Sylhet.
Excellent.
Yeah.
Well, thank you. Thanks for joining us.
But he's at Lamont for the next 7 months.
Oh, yay.
So he's here in New York now.
Thank you.
So come up and visit.
I need to come up and visit. Yeah, I'd love to. That'd be great.
So that's so great. As I mentioned in the text, Shukru, that how do you call Muhammad or
No, just Shofik is better.
Okay, okay. So I think I'm happy to invite you if you can give any talk. We need that kind of colleague from that local region. Any topic, environmental change over the Ganges Brahmaputra Delta will be nice. So I think Michael will support you.
Yeah.
So think about, if you feel comfortable, give me a talk. I have a schedule. Okay?
Yeah, I am doing work on just river dynamics on Upper Brahmaputra. If it will be finished, so I will let you know.
Sure, that's good. Maybe end of your visiting, in the end of the 7 months, you should give a talk.
Yeah, that'd be great.
Is this a deal?
Although we're mostly working on the tectonics together.
Oh, okay, that's cool. So any other? So Carl, I want to see now. I know you also work on the Mississippi River. So talk about the channel. Talk about the lowland. I guess that's a big difference. Compare the low Ganges and Brahmaputra and the Mississippi River, right? So what?
It's funny you say that, because yes, there are differences, but there are a lot of similarities too.
That's good to know.
Yeah, it's so what I was talking about earlier, where we had that fluvial to tidal transition, and you have like the fan delta, and then in the backwater, the channels get isolated. Well, it's very similar to morphology here in the Mississippi, where we have distributary channels, interdistributary basins. They're very muddy. I think the biggest differences have to do with just the magnitude of the discharge. So because this isn't such a sand dominated system, we don't have as much sand stratigraphy. So the sand is very isolated to those channel distributaries. And like those interdistributary basins are very muddy, and they're very muddy at depth. So while in the GB, it's really sandy stratigraphy at depth. In the Mississippi, it's really muddy.
But both have a high subsidence rate.
Yes, they do. In fact, it's interesting. I think the rates that we're seeing are very similar, actually, like beyond those hinge zones. And like as you go to the edge of the delta, it's about 6 to 11 millimeters a year here. And I think that's what we're measuring in the GB, right, Mike?
Yeah, if you include all the shallow subsidence. One other difference is you only got one tiger at LSU, and there are a lot more tigers in Bangladesh.
That's right.
Good. And and also the storm, the hurricane or tropical storm is
Right. So the GB is like the tides, right? That's the big mechanism of getting the sediment around. Here in the Mississippi, we have a micro tidal range. There's no tide.
Our river dominated.
Yeah, very river dominated. But that also means that those storms, Gene Turner here would argue, oh, hurricanes are the only thing that's keeping our wetlands alive. And I think people would debate, it's many things, right? You got to have the sediment coming in from either storms or the river, but we have a lot of organic production too. These are very organic marshes here. Like our wetlands, we have peats that form from the marsh plants, and those peats don't decay because we don't have the tidal fluctuation.
That's another challenge.
So that organic contribution here is much bigger, much bigger.
Interesting.
So if we think about so actually Jeff Boehmer did a comparison of carbon sequestration.
Yeah.
So here we have a lot of carbon sequestration because there's a lot of organic production and it gets preserved. The GB has a lot of carbon sequestration because even though there's not as much carbon preservation, the sedimentation rate is so rapid. It's like more material is coming in that you end up with a huge amount of carbon being sequestered there as well. So it's two deltas, same story, but different mechanisms.
That's good. Because of the tide, that could be the the burning rate could be very high over the GB. So we didn't see too much accumulate over there, but doesn't mean the contribution, is less.
Right.
So that's need more study, do a comparison. For example, even the carbon export to the ocean between Mississippi was the GB. That could be very interesting.
Right, that could be excellent. There's a student, I don't know if any of you all know, her name is Kendall Valentine. She just got her PhD here at LSU with Giulio Mariotti, and she now works at VIMS doing her postdoc with Matt Kerwin. But she's very interested in this carbon sequestration and also release, like as marshes deteriorate or wetlands deteriorate, how much it gets released to the coastal ocean. So I think she's doing a paper right now, kind of like a compilation of everything from the world.
Similarly, thing could happen like the Irrawaddy in the Andaman Sea because the macro tide so strong exchange every day is burning, remixing. That's a very, but anyway, interesting.
Yeah, I've never been to the Irrawaddy. I'd love to see it. Like I feel like
you should. We should.
List is to go to every delta on Earth if I can.
Yeah, hopefully next, after this summer, we are free to go. And also now Myanmar, the situation, I don't know.
Oh yeah, okay, that's true. Myanmar might be off the books, but we'll see.
Anyway, problematic for the next little while.
Yeah. I think that situation may not that bad, but anyway. So thank you very much. I think this is a great dialogue. I think we need that kind of, brainstorm, and this is actually the very good part of this talk series. I think
I love it. Thanks again, Paul, for having me.
All people will watch your talk offline on the YouTube. And okay, think about that. If you talk about the Polder River and to the student, if you give them 5 talks we already had, they have everything. From Michael Stigler, from Stigler Brad, from you, from Robert Nichols, that's just...
Well, I teach a Delta geology class. Maybe next spring I'll be like, just watch YouTube. It'll be fine.
That's actually what I'm doing now. Okay. Okay.
Great.
Cool.
Well, good to